Okay, so guys, in this part of chapter 14, I want you to differentiate between the conservative forces and the forces that are not conservative. You have to know that the weight and the elastic force are both conservative because they only depend on state 1 and state 2. The first and the last states, it doesn't depend on the path followed by this particle or this body. However, the friction is not a conservative force. Now, if I have only conservative forces, like the force of the weight and the force of elastic, or the elastic force, the force of the spring, then you can apply conservation of energy. And what is the equation of conservation of energy? The conservation equation of energy, of mechanical energy, states that T1, which is the kinetic energy at 1, plus V1, V here is not the velocity, it is the potential energy at 1, is equal to T2 plus V2, and it's equal to constant. This is in fact the mechanical energy between state 1 and state 2. Let's apply this equation on this problem. I have a 5 kilogram scholar that has a velocity of 5 meters per second to the right when it is at A. So when it is at A, this is the velocity, right? When it is at A, the velocity is equal to 5 meters per second, which means I can find TA, all right? So from this velocity, I can find the kinetic energy at A directly. I have mVA squared. It then travels along the smooth pipe. Determine its speed when its center reaches point B. So I need to find VB. How to find VB? If I know TB, I can find VB. And the normal force it exerts on the road at this point, I'm going to also find the normal force that could be to the left or to the right, all right? Because I have two normal forces. I have two supports here that are restricting the scholar. So in fact, I can assume any direction, and then I can find out if this assumed direction is correct or not. Now, there is a very important sentence here. They are saying that the spring has unstretched length. So L0 is equal to 100. Why is it important to know the unstretched lengths? Because in fact, I know that V, the potential energy, is half AS. And what is S? It's L current minus L0, right? Because I know that S is L minus L0. So that's why it's very important to know what is L0. So in fact, guys, it's very clear that I need to do the conservation of mechanical energy since I don't have a friction force between A and B. So I'm going to apply the conservation of mechanical energy, and you can also, of course, guys, apply the work and energy principle. You're going to have the same answer, okay? So it's between A and B. Now, what do I have at B? At A, sorry. I'm going to start by A. What do I have at A? At A, of course, I know TA because it's given, VA is given, and I know that I have two forces. I have at A, whenever I am at A, the spring will be like this. So I have the elastic force and I have the weight. Now I'm going to start by the potential energy of the weight at A. What is the potential energy of the weight at A? It's mgHA. So in order to find the potential energy of the weight, I have to specify the datum in order to find it. And I'm going to stick to this datum in the problem, all right? So I cannot change the datum between A and B, all right? So I'm going to assume that this is my datum, all right? I'm going to assume that this is my datum, and then I can find the potential energy at A, right? So what will be HA? HA will be equal to 200 millimeters because this is a circular path, right? So it's mg times 0.2, and it's of course positive because it is above the datum. Now, I also have another potential energy at A, and this is the elastic potential energy at A. This will be equal to half K S squared. And what is S? It's L minus L0. So it's LA minus L0. All right, what is LA, guys? It's the current length at A. So what is LA? This is LA. What is LA, guys? What is the current length of A, of the spring at A? Guys, I know that this is 200 millimeters, and I know that this is also 200 millimeters. So yes, LA, I'm gonna duplicate this. Sorry, guys. All right, so LA will be equal to radical 0.2 squared plus 0.2 squared. And this means, guys, that it's equal to 0.28. And this means that SA, which is LA minus L0, will be equal to 0.28 minus L0, which is 100 millimeters. This means that it is 0.1 meters. So L0 is 0.1 meters, all right? Don't forget that it is given in millimeters. And this means, guys, that SA is equal to 0.18. All right? So now I can find V elastic at A. V elastic at A will be equal to 0.83 joules. Now, what about B? What about B, guys? What are the potential energy at B? In fact, at B, they are not all equal to zero. The potential energy of the weight is equal to zero. It's not elastic, no, Abbas. It's only for the weight. Why it is equal to zero for the weight, guys? Who can tell me why is it equal to zero for the weight? Because it is at the datum. Because it's at the datum. Don't forget that the datum is at B. So V gravity at B is equal to zero because B is at the datum. B at datum. So don't forget that I took the datum at B. And V elastic at B will be equal to the same, half KSB squared. Right? Which is half K LB minus L0. Now what is LB, guys? LB at this position, this will be the spring, all right? So LB will be 0.2 plus 0.2, which is, sorry, this is squared, which is 0.4, all right? So it's half K 0.4 minus 0.1 squared, which means 0.3 squared, so it's equal to 2.21 joules. Now, guys, I can conserve the mechanical energy. So TA is a given, plus VA, which is the sum of both gravitational and elastic force, potential energy, is equal to TB plus VB, all right? And then this means, guys, that half M, which is 5, V squared, which is 5, plus 9.81 plus 0.83 is equal to TB that I need to find half 5 VB squared plus the potential energy at B, 0 for the gravitational force, 2.25. And then this means, guys, that VB will be equal to 5.325. Now, guys, I want you at home to apply the work and energy principle. All right? So if you apply the work and energy principle, you have to find the same answer. Okay? Now, am I done yet? No, because the question is also to find the normal force it exerts on the road. It's easy because, in fact, I know that at B, what are the forces exerted at B? I'm going to take this as my normal force and this as my spring force. And I know that A normal is equal to V squared over rho. So don't forget, guys, that spring force is Ks, all right? V squared over R, which is here. What is R, guys? R is 0.2, 200 millimeters. All right? So I know that F spring plus N. Of course, you can take different direction for N, and then you can conclude if your direction is correct at the end of the problem. mv squared at B that I found earlier over 0.2. And I know that F of the spring is K times SB plus the normal force that I need to find is equal to this one. And I know that SB is equal to 0.3. Then you can find the normal force. It's fortunately positive in my case, and it's equal to 694 Newton. Any questions, guys?